So now that we've had a little bit of introduction to vectors, let's talk about vectors in the plane. There are some different things that we like to do with vectors, and the first thing we're going to talk about is the idea of a unit vector. It's called a unit vector because it has a magnitude of 1 unit. And we take our regular vector and we divide by the magnitude of the vector. You can think of it this way, or if you want to think of 1 over the magnitude multiplied by our original vector. This goes back to some of the things that we've done in trigonometry when we talk about a unit circle. Think of a unit vector in the same idea. So here's my vector, and I want to turn it into a unit vector. So the first thing I have to do is I have to find the magnitude. So I'm going to square this, and I'm going to square this, and add them up. That gives me 29, or the square root of 29. So that's what's going to go on the bottom of my vector. So I have 1 over the square root of 29, and I have to multiply that in to my original vector. When I do that, I get negative 2 over the square root of 29, 5 over the square root of 29. That's the same vector as v in the same direction, except the magnitude has been shortened to 1 unit long using those coordinates. Now sometimes you'll see them get the square root off of the bottom because we know we're not supposed to have that square root. If I get that square root off the bottom, you may see this also written as negative 2 square root of 29 over 29, 5 square root of 29 over 29. But that's now a unit vector. The other thing we talk about with unit vectors, whether we're talking 2 dimensions or even if we're talking 3 dimensions, is you'll see this notation. So this is a lowercase I. So this is the x direction. You think of your xy, this is 1 unit long in the x direction. This vector is in the y direction, and again, 0, 1 would be 1 unit long in the y direction. So sometimes we'll use unit vector notation with this I and this j. So here's an example. My initial point is at 2, negative 5. My terminal point is at negative 1, 3. I subtract my x's, subtract my y's, and I get negative 3, positive 8. You might see it written this way instead of this way. They mean the exact same thing. This is my x direction. This is my y direction. They may even write vectors this way and then have you do vector operations. So they want me to double vector u. They want me to take v, vector v, times negative 3, and they want me to add these 2 things up. Okay, I add the I portion, this is the x part. I add the j portion, this is the y part. And I have a vector. It would be the same as writing it with these angled brackets for my x and y direction. The next thing we want to talk about after unit vectors is the idea of direction angles. When we talk about vectors, we talk about magnitude and we talk about direction. So if I have vector u sitting in standard position, I go so far in the x, so far in the y, and that determines my vector. But that vector makes an angle with the positive x-axis here. That's its direction. That's how we normally mark its direction. And the interesting about this is the x direction corresponds to cosine, the y direction corresponds to sine. So whether you think of the vector this way, or you think of the vector with unit vector markings on it, it's the same thing. So if we have an example here where vector v has a magnitude of 3, and this angle is a 30-degree angle, if I want to determine the vector, if I want to determine the components of this vector, I take the magnitude times the cosine of 30. That gives me the x direction. I take the magnitude times the sine of 30. That gives me the y direction. And now I have that vector based on the direction that it's pointing. The other nice thing about this is we already know the magnitude. It told us it was 3. But that angle, if I wanted to get back to my angle, I could use tangent, which is sine over cosine, and in this case, y over x. So if instead they gave me something like this and asked for the angle, I could figure that out. So I did an example based on that. Here's what they gave me. 3 in the x direction, -4 in the y direction, and they want to know the angle that this makes with the positive x-axis. Now, if you are visual, let me draw this for you. We're going to go 3 in the x direction, -4 in the y direction. So here's my vector. They want to know what angle this makes with the positive x-axis. So I put the y on top, the x on the bottom. That's what this is saying right here. And of course, I have to do inverse tangent of that to get my angle out. And it turns out this angle is 53.43 degrees. Now, this is useful for things like bearing, if we're talking ships navigation or plane navigation. This is useful for finding angle of forces. There's a lot of practical applications, but this idea right here is going to help us with direction angles. So let's take a look at this example right here. It says an airplane traveling at 100 miles per hour at an angle 30 degrees below the horizon. So here's my plane. It's moving at 100 miles an hour and it's 30 degrees. So if we talk about bearing, we're basing that off of this direction, or if we base it off the positive x-axis, we're talking 210 degrees. So if I take what I learned with this direction angle, if I have a magnitude of 100 and I multiply that by the cosine of 210 degrees, sine of 210 degrees, I can give you the component forces, the pieces, that determine where this airplane is going. Now again, if you wanted to, I could write it in unit vector notation. This is the x direction. This is the y direction. So now that we've looked at an example where they gave me the angle, they gave me the magnitude, let's look at a practical application. So here's a picture of a boat sitting on a boat ramp. The ramp has a 15-degree angle of elevation. There's a truck holding onto this boat in its trailer, and it takes 600 pounds of force to keep that trailer from going down the ramp. So there's a lot of things going on here. Now, when we talk about how heavy this boat is, this boat, weight, trailer, gravity, everything pulling it straight down. But those two forces are split. One of them goes into the ramp, and obviously the ramp pushes back. That's why the ramp doesn't collapse. And then there's a force that's pulling it down the ramp. And that's the force that we're overcoming by pulling it up the ramp. So we want to break this into its forces and only look at the one that we're really concerned with. And in this case, we're trying to find out how much this boat and trailer truly weighs. So we're not going to look at both parts of it. Now, if I put some names on here, this is the force against the ramp. We're not really worried about the force against the ramp. This is the weight. This is what we're trying to figure out, how much this thing actually weighs. And then there's this really small force. This is the force to move the boat. It's the force that pulls the boat down. It's the force that we're pulling up. We're trying to find out weight, so we're going to use this idea of the force against the ramp to figure it out. So I'm only going to use part of this. The horizontal, they they talked about. What we're looking at is we're looking at vertical. So we've got this 600 pounds, and we're looking in the vertical direction. So we're going to take the magnitude, which we don't know, the weight, and we're going to multiply it by the sine of 15 degrees. So this 15 degrees here gets projected in here. So that's what we're looking at. We're looking at that 15 degrees and trying to figure out what this boat actually weighs. So if we solve this, and we divide this out, we will find out what the weight of the boat actually is. Now, this one's in our textbook that we're using, and it turns out that this boat weighs, with trailer, 2,318 pounds. And we figured that out based on how much it takes to keep it from going down and the angle of elevation. A similar example, another practical application is this one right here. So we have this airplane. It's going 500 miles an hour at a bearing of 330. Now, bearing isn't useful for us, so I took that bearing of 330 and I changed it to 120 degrees. Again, we're looking at the angle that's made with the positive x-axis. So we're looking at a 120 degree angle. We also have a wind that we encounter that's going 70 miles an hour, and here's its bearing, north 45 degrees east. The nice thing about 45 degrees on a bearing, it also makes a 45 degree angle with the x-axis. And we're trying to find out how fast we end up going as a result and what direction. So if I put this wind in here, that wind is actually going to push my airplane a little more this direction, and it's going to actually push it a little faster in the y direction, but a little slower in the x direction. So let's lay these out. First, we'll talk about the plane. The plane's going 500 miles an hour. We know we have the cosine of 120 degrees. We have the sine of 120 degrees. So if we want to talk magnitude, we multiply that in. We're going to get our two parts to this speed. And I'm going to leave the square root of 3 in there. Now, it might seem strange that we're going negative, but remember, x for us is positive that way, and we're actually going this way. That's why this is a negative direction. So don't let that negative throw you off. Y is positive because it's going in this direction. Now, if we look at the wind is blowing at 70 miles an hour, and we're dealing with a 45 degree angle. So we got cosine of 45, we've got sine of 45. I know I'm running out of screen here. So when I multiply those two in, I get 35 square root of 2 and 35 square root of 2. So you can see what's going to happen here. If I take this and add it in, I'm going to be going in that direction much faster. But if I take the 35 square root of 2 and compare it to my x direction, it's going to actually slow me down. So that wind is going to have an effect on me. So I'm going to have a resultant of negative 250 plus 35 square root of 2 in the x direction. I'm going to have a 250 square root of 3 plus 35 square root of 2 in the y direction. Now, I can do the calculation for magnitude. I can take this, square it. I can take this, square it, add them up, square root it, and it turns out that my magnitude is going to be 522.5. If I go back to my original problem, this is miles per hour. So even though that wind is acting on my plane and slowing me down in the x direction, it's actually making me go faster in the y direction. And overall, I'm going 522 miles an hour, even though the plane itself is only going 500 miles an hour. If I take my calculation from the direction angle, if I want to find the angle that we end up going, we're going to do the inverse tangent, and we're going to put y over x of our resultant vector, and we're actually going 112.6 degrees. So this is 120, this is 45, so it's working against it. So our plane actually ends up going a little different angle, but a little faster than what we have on our speedometer. So we end up with a magnitude of 522.5 miles an hour in a direction of 112.6 degrees from the positive x-axis.